Special Powers and fellow Embry-Riddle aeronautical eagles, this is my Mooney M20J presentation, which is narrated by Michael Orff. This presentation is an in-class documentation for specifics for aerodynamics and performance of the M20J. Instead, if you want a compromise between speed, economy, and payload, the Mooney M20J model is the two-person flight machine for you. The Mooney 201/M20J, between the years 1977 and 2008, almost 22,000 Mooney M20Js were produced with propeller-driven general aviation customers. The Mooney M20J is an excellent aircraft, as it's known also as the Model 201 for its impressive top cruising speed of 201 knots. This slide is the Mooney M20J's manufacturing specifications. As requested for this assignment, the max weight is 3,000 pounds, which does not reflect the real max weight of 2,740 pounds for the M20J. The Mooney M20J has a NACA 63 TAC 215 airfoil. Main airfoil for the Mooney M20J NACA 63 215. Stall angle of attack associated with CLmax is 15.5 degrees. Zero lift angle of attack is -3 from data from CLV alpha from figure 3. The CLV alpha shows angle where zero lift is performed. Comparison of my airfoil to a symmetrical airfoil, we learned from the text that a symmetric airfoil produces zero lift at zero angle of attack. My airfoil is Compartment, so it produces lift at 0 degrees angle of attack and below. This is table 2.1 for the standard atmospheric table. Calculated airspeed. We'll use table 2.1 from page 16 of our textbook with 1,000-foot pressure altitude for calculation. For table of the density, altitude is 0.9711 at 1,000 feet. I was told to utilize 3,000 for weight. The max gross weight is 3,000. Area of wing is 175.7 square feet with a CL max of 1.5. Then we use the velocity formula, and as you see below, it's 58.8 knots. We learned with the pilot's handbook from the M20J stall speed clean 62 knots with a 3.2 knot difference, and must take into account the shape of the airfoil at the tips. For our wing design, it stalls at root first. This is why the M20J is a good pilot training airplane. How does lift change with airspeed if a constant angle of attack and altitude are held? Lift is proportional to the square of the aircraft's velocity. So if the angle of attack stays the same, but you double the speed of your aircraft, your lift will increase by 4 times. For my example, with my data, I will use 50 and 100 knots at pressure altitude with a standard temperature and a CL of 0.5. Dynamic pressure came from our table 2.1 from our textbook. As you see, 50 knots is 722.975 pounds of lift, and 100 knots is 2,891.90 pounds of lift. The square root of 289.1 is 53.77. This is pretty much the square of the speed, which shows an accurate assumption for the airspeed if it is doubled. Here again is table 2.1 from our textbook. How does lift change with altitude if a constant A, and airspeed are held. Using the same data for 100 knots, we will change in altitude and change density-altitude ratio for an altitude from 2,000 per table 2.1 from our textbook. As you see with 100 knots, it's 2891.90. And also with 100 knots, but with 2,000 foot pressure altitude, it's 2,807.65 pounds of lift. This shows when an increase in altitude, there will be a decrease in lift. The decrease is roughly about 84 pounds of lift, which is an increase from the 100 foot pressure altitude. How does the required CL and angle of attack for your aircraft at a weight change with changes in airspeed? So with velocity, we're going to use the 2,000 feet in altitude table 1, which is 0.9428. We're going to use the empty weight of 2370 for the Mooney M20J at that 200 feet of pressure altitude. With CL max of 1.5, the area of the wing is 175.7 square feet. We do the formula, and we see our speed is 53.04 knots. Now we're going to use 3,000 pounds for the weight, and we see that you now need 59.68 knots. You see the empty weight of 2370, we need 53 knots for a stall speed. With a weight of 3,000 pounds, we need 59.68 knots for stall speed. So we see at the same altitude at two specific weights, with higher weight, higher speeds are required for the required CL and angle of attack. What happens if the required CL is large than the CL max of the airfoil, and what speed is usually associated with that condition? The stall is where the angle of attack increases beyond a certain point when lift starts to decrease. If the coefficient of lift, CL, is larger than the CL max of the M20J airfoil NACA 63-215, the wing would be considered stalled. You would lose a boundary layer of air which would completely separate from the M20J airfoil. The center pressure is working against the lift vector and no longer behind the lift vector but in front. Please refer at the CL max 1.5 from previous questions for my calculation. Drag. Here is the M20J drag chart data from various knots from 30 to 170. Here, it's charts and graphs dealing with drag for the Mooney M20J. What are the minimum drag parameters for the M20J? Use the following formula for the weight of 3,000 pounds. Then you look on the chart, in CLDL, you take that 15.24636, and it will equal 196.76. The speed minimum would be 89 knots as we found on our chart in table 1. What is the maximum lift to drag CLDL parameters for the aircraft? The CLDL max value is 15.24636 found on table 1. speed at which the CLD max occurs is 89 knots, also found on Table 1. Compare answers A and B. Let's see what we found. So both A and B came to the same answer. Minimum drag at CLD max value is where the aircraft is the most efficient, which is 89 knots. For the Mooney M20J, 89 knots appears to be the crucial speed. Explain which of your delivered values will allow glide scope predictions for the aircraft and the best glide scope with the values. Knowing the minimum drag of the M20J at 80 knots is crucial. For the specific values for the drag speed, we can use this knowledge to descend our M20J at that speed. Unaccelerated performance. Mooney M20J is powered by the Lycoming 360 Alpha 1B, which has a horsepower rating, as you see, at 200 horsepower. The following is the graph and diagram which shows the total drag, induced drag, parasite drag, and the blue shows the power required for the certain velocity for KTAS. Mooney M20J, power required, power available. It's the chart. Maximum endurance air speed is the amount of time an aircraft can remain airborne. To do this, the minimum amount of fuel must be burned. The fuel flow burn rate depends on the power required to gain the maximum endurance airspeed. The aircraft requires the least amount of power required, PR. With gain the most endurance. The Mooney M20J at a weight of 3,000 pounds, the maximum endurance airspeed is 65 knots, which has the maximum required power of 47.20 horsepower. Maximum endurance is CL, as you see with the formula here, is 65 knots. And we'll check the formula values for 70 knots. You can clearly see the formula works at 65 knots as the maximum endurance airspeed. Best climb conditions. Best rate of climb with associated airspeed. PR 53.88, pressure altitude 210 with a weight of 3,000. Rate of climb is 33 with PR minus PA and the weight. So the best rate of climb for the Mooney M20J for the following data is 1,717.32 feet per minute. My power required is off the CLDL max for the M20J, which is the most optimal. Best angle of climb and associated airspeed. Pressure altitude of 210. Power rating of 53.88. 83 knots for velocity. Weight is 3,000 pounds. Use the following formula, and we find that the best angle of climb for their associated values is 10.95 degrees. Maximum forward airspeed. We can determine the maximum forward airspeed by knowing the horsepower of the airplane and using the chart to the right of the M20J as a power plant of the Lycoming 360 Tech Alpha 1B6, which has available horsepower of 200 horsepower. For the performance data we have for this exercise, the maximum forward airspeed is 165 knots. This is because to achieve 165 knots, you need 187.31 horsepower. We can't go to 170 knots due to the power available of our power plant is 200 horsepower. And with the performance data on the chart, 170 knots takes 203.08 horsepower. Best glide airspeed. To achieve best glide airspeed, we must flown at the airspeed corresponding to the LD max ratio. We have already found the CDL max ratio. Please see following chart. The max CLDL is 15.25, which gives us the best glide scope of 89 kts. Examination of takeoff and landing. Takeoff and landing performance. As you can see from the provided data from figure 10.1, aircraft weight directly affects the required takeoff speed to the aircraft. For example, let's look at the lowest weight of the aircraft versus the highest per figure 10.1. For ease, you can see below in the blue, the lowest weight of the aircraft is 26,000 weight in pounds. For the chart, we can see we need 63 knots or 72 miles per hour of liftoff speed. We also see to clear an obstacle at 50 feet, we need a speed of 68 knots or 78 miles per hour. For ease, please see below, marked in blue on figure 10.1. Takeoff distance graph. The following is a takeoff distance graph from figure 10.1. We're going to use a pressure altitude of 2,000 feet, 22 degrees Celsius, with a weight of 2,600 pounds, 6 mile per hour headwind. All right, now you can use your chart, bring it over, and you see you need 600 for a takeoff roll. The distance that the aircraft was covered was referred to in the red, with the temperature being 22 degrees. And you saw we drew a line straight up to 22 or 2,000 feet. We then went over horizontally to our desired weight of 2,600 pounds. Then we continually went over to the right. We saw the horizontal direction of the wind speed of 6 miles per hour. We then proceeded to the right in a horizontal position to see our final answer of 600 feet takeoff roll. Landing complete using specific aircraft data for the M20J. All right, so for the aircraft weight of 3,000 pounds, takeoff 2,900 pounds. Assumption is 100 pounds of fuel burned during flight. So you take 3,000 minus 100 and you get 2,900 pounds. Now the weight 1 is 3,000, weight 2 is 2,900. That's weight after burned fuel. B1 is 58.8 knots. stall speed from table 1, drag during landing of the M20J. Now we take the following formula and we see with the corrected weight with a fuel burn we need 57.8. So assuming fuel is constant, using the common factor used is 1.2 times stall speed. So the stall speed now is 57.8 with a selected landing weight of 22,900 pounds. Now you take 1.2 times the 57.8 and you get your new approach stall speed of 69.36. Drag during landing, total drag at touchdown, average drag during landing roll. All right, so we go back to our table here. And then from previous calculated data, drag during landing, so 58.8 knots, stall speed, 267.07 is total drag at touchdown, as you can see for the DT in the chart. Average drag during landing roll based on the total drag. Average drag over the entire landing roll. You can use 50% of the total drag at touchdown. So weight is 3,000 pounds. Total drag at touchdown is 267.07. The 267.07 divided by 2 is 133.535. So 133.5 is the average drag during landing roll. All right. Residual power based on the rating power of the aircraft. Per MSIC core concepts, residual thrust in idle during landing is usually equal to 10%. Per slide 10 parameters, horsepower of the M20J is 200 horsepower. 200 horsepower times 0.1 is 20 horsepower. The 20 horsepower is the M20J's residual power. All right. Factors such as 1.4 times the idle thrust at touchdown. Notice the relationship here is proportional to the velocity, not directly proportional to the velocity squared, such as drag. Therefore, it is also not in a linear relationship with landing roll distance, and the 1.4 only a rough estimate. So using the following equation, you see we have 110.5 horsepower thrust at touchdown. Average thrust during landing roll is power divided by V. So you do 110.5. So you get 154.7 average thrust during landing roll. With a touchdown speed of 69.36 knots or 79.82 miles per hour, or 117.1 feet per second, and a time stop of 5 seconds. Use the formula here. So negative 23.42 is the average deceleration during a landing roll for the M20J. Length of landing roll equation right here. So once you plug in all your figures, you'll see that you need 293.342 feet for a landing roll. Difference between landing roll as calculated above and landing distance as published in the pilot's operating handbook. So right here is from the M20J's pilot operating handbook. So landing gear down, wing flaps pull down. According to pilot's handbook, see here, at sea level and at 2,000 feet pressure altitude. So a ground roll for sea level is 956 feet. but with a 2,000 foot, you need 1,118 grounding roll feet. As you can see, with a change in altitude will increase in change in density, altitude, pressure, and temperature, as seen from 10.1 takeoff distance graph. Any one of these directly affect ammonia M20J's performance. Influence on landing speeds. The effect of altitude also has great influence for the performance of the aircraft. When an increase in density altitude increase the landing speed, indicated airspeed will remain the same, but the true airspeed increases. Basically, a decrease in density will decrease the aircraft stall speed, but an increased pressure or altitude will result in an increased stall speed. Influence on landing distances. Well, increase in altitude makes the density altitude higher, which will make the aircraft not perform as well and need an increase in landing distance. When the altitude goes lower for other airports, the density and altitude will lower as well and require a decreased density required for landing. Limits of landing, such as runway material and surface conditions, run slope, and wind conditions. Runway material all have different frictions. Grass has a different friction than concrete. For a runway material with more friction, with no contamination per Federal Aviation Administration Advisory 25.3 would have a shorter landing distance. With surface condition, with the category of contaminated runways per the FAA, surfaces that are contaminated that cause less friction, like water with hydroplaning, will cause a unstoppable landing condition or need for a longer landing distance. When runway slopes, when a pilot needs to take land, has impacts on required stopping distances. With the performance of the airplane going uphill while landing uphill reduces landing rollout. Going down it will increase it. The slope of a runway greatly influences the impact of the stopping power of the aircraft. With wind conditions, the tailwind will increase the landing distance because it increases the velocity of the aircraft. The following formula is to correctly calculate for a tailwind. With headwind, it decreases the landing distance because it decreases the velocity of the aircraft. The following formula is the correct way to calculate for a headwind. Maneuver and performance. The following are the parameters for the M20J aircraft. The following were the limitations and load factor limits for the M20J aircraft per the pilot's operating flight manual or handbook. All right, so taking the MAX 2, weight of 3,000 pounds with a CL max of 1.5 and all the following parameters. Positive, negative, limit load factors, stall speed. We use the following to see the different G ratings for the M20J. Using the following formula, you'll see for positive, for 1G is 57.9, for 2G is 81.9, and for 3G it's 100.369, and for the max 3.8 it's 112.962 KEA. Now go into the negative for the M20J using the same formula of negative 1G is 57.94, and the max of 1.5G is 70.9718. And then you can see the same on the chart here with the positive and negative of G's for maneuvering speed required. From the VG diagram, slide 6, Moon M20J has to fly. Be safe in accordance with G values in the stall to the right of the curve. The pilot flies to the left of these curves. They have gone past the aerodynamic limits of the aircraft, and the aircraft is in the stall region. If the pilot chooses to exceed the unlimited load factors, it can lead to catastrophic failure to the airframe. As per the textbook discussion 235, the unlimited load factors are 1.5 is the limiting load factors. Here's the limited load factor. So we do that, and we see the Moon M20-day unlimited load factor is 5.7 Gs. And you take that unlimited load factors by the specific weight of 3,000, and it's 17,100 pounds. So the positive unlimited load factor of the aircraft weight of 3,000 is 17,100 pounds. Maneuvering speed. Look back at slide 44. You'll see with 3.8 Gs, maneuvering speed is 112.962. We see our manufacturing speed is 112.962, or roughly 113 knots rounded up. Bank angle associated with a positive limited load factor. So, using the following formula, the bank angle associated with the limited load factor of 3.8 is 74.74. All right, now into the rate and radius formula. So, using the following formula here, from previous data provided, we see the ROT is 5.576 degrees a second. So, take that data, and we can see our radius is 1,963 feet. All right, now we go 100 through here so you can visually see. All right, our aircraft maneuvering speed is 112.96. To use the turning performance diagram you see in blue, we found our maneuvering speed of 112.96, and then went horizontal until we found the first 30-degree bank angle for the turn radius marked in yellow, and then we went straight down in the green, and we'll get approximate radius of turn 1,965 feet. If you went to the second 30-degree mark with the red line, you will see the second yellow 30-degree, which will give you the approximate rate of turn of about 5,500 feet outlined with a purple line with the data provided. Bank angle of G relationship formula. Using the following formula for the cosine, the bank angle associated with the positive limiting load factor of 3.8 G is 74.74 degrees. Bank angle to G relationship, turn rate and radius, stall speed under elevated G bank. So this shows here stall speeds with different bank angles. So you can see with a 30-degree, stall speed is 41. With a 45-degree, stall speed is 45 knots. And then for a 60-degree, stall speed is 53 knots. All right, so rate of turn. So the following equation is used for the rate of turn. Plugging in the data from previous diagrams and slides, using the rate of turn formula, we can see for the Mooney M20J, the rate of turn is 5.576 degrees a second. All right, the following is necessary aircraft limiting load factors, positive, negative, for my aircraft for the assumed weight. So this is which in the pilot operating handbook shows what the maximum load factors are. So limited load factors, the positive and load factors for the M20J pilot operating handbook is 3.8 Gs to negative 1.5 Gs for our class assumed weight of 3,000 pounds, which was used to calculate these load factors for the M20J. All right. Now we can see positive using the unlimited load factor here, 3.8, the unlimited load factor of 1.5, we have 5.7 G for the unlimited load factor of 17,100 pounds. We can use this unlimited load factor to find the limited load factor by taking the unlimited load divided by 1.5, and then we can see that the limited load factor is 11,400 pounds. We can use the limited load factor to find a pre-calculated limited load factor. So we take the limited load factor, divide by the weight, and we get 3.8, which is just to make sure we're correct with all our formulas and charts. We do the same thing for the negative, same formula, and then we see that it is like we saw in our pilot operating handbook of negative 1.5 G for the Mooney M20J. Next is weight and balance for the M20J aircraft. The following 5 slides are from the Mooney M20J Pilot's Handbook for the required forms and data to perform a proper weight and balance. This is helpful information from the Mooney's Pilot Operating Handbook to a 7-step guide for calculating a load for your aircraft. Ms. Cindy Hallman covered from the video that the owner's weight and balance form is required for the weight and balance. And this is a blank weight and balance sheet from the Mooney M20J Pilot's Operating Handbook. Ms. Cindy Hallman covered from the video that we have datum lines. Class here is our Mooney M20J datum line. For the referenced M20J Pilot's Operating Handbook, the highlighted in red is our aircraft datum line 0. as Miss Cindy Hallman described in the video. Anything forward of the datum line towards the engine compartment for the Mooney M20J would be negative. Behind the line would be a positive value. Class, this is what Cindy Hallman described as graphs to calculate our Mooney M20J aircraft if it is not too nose heavy or tail heavy from our pilot operating handbook. Class, this slide covers the maximum weight limits of the Mooney M20J aircraft for the aircraft pilot's handbook. Class, this is our Mooney M20J assumptions when it comes for this assignment. Now to what we have to consider for weight and balance on our Mooney M20J. Ms. Cindy Hallman stated we have to consider the following. Front seat passengers left and right weight. Rear seat passengers left and right weight. What our fuel weight is, which for the Mooney M20J, the fuel tanks are on the wings. And lastly, the weight of the baggage compartment. Ms. Cindy also described, after we found the weight and balance, we need to find the arm distance for that weight, which is also known as the distance from the datum line. For ease for this presentation, I'm going to use the Mooney M20J weight and balance calculator to find real scenario arm lengths. The arm length for the front left and right passengers is 36 inches. For the back seat passengers, it's 70.7 inches. For the fuel tank, it is 48.4 inches. For the baggage compartment 1 is 95.5 inches. The Mooney M20J does have a second baggage compartment, but for this presentation, there is no weight for this area. Now that we have our arm distances from the Mooney datum line, let's add all the weight so we can have a visual for both arm and the weight. The following is the weight for each arm. The front seat passenger left and right weight is 240 pounds. The rear seat passenger's left and right weight is 200 pounds. The fuel on the wing weight is 384 pounds. The weight on the baggage compartment is 50 pounds. To calculate the Mooney M20J center of gravity, we use the following formula. Weight times arm equals moment. As Cindy Hallman explained, to get the total weight, you add the empty weight, which for us is also the oil weight, the front seat left and right weight, the fuel weight, rear seat left and right weight, and the baggage compartment weight. Then you multiply the arm and you'll get each moment. Now to calculate the following moments we added to the weight of the Mooney M20J. The front seat left, we take 140 for our weight, times it by 36 for the arm, and we get 5,040 inch-pound for the moment. Front seat right, we take 100 for the weight, times by 36 for the arm, and we equal to 3,600 inch-pound for the moment. Now for the fuel tank. We take 384 weight times the 48.4 arm, which equals 18,586 inch-pound for the moment. Now for the rear seat left, we take 100 for the weight, times it by 70.7 for the arm, and we equal 7,070 inch-pound for the moment. Now for the rear seat right, we take the 100 for the weight, times it by 70.7 for the arm, and it equals 70 inch-pound moment as well. Finally, for the baggage compartment 1, we take a 50 pounds weight, add it to the 95.5 arm, and it equals to 4,775 inch-pound for a moment. Now to the next slide to see these weight inputs from the passengers, both front and back, the fuel, and the baggage compartment, and how it's affected our Mooney M20J center of gravity. To calculate the M20J total weight, we add up all the weight, as seen below. The total weight from our inputs now is 2,853 pounds for the Mooney M20J. To calculate the total arms, you add up all your arm lengths, as seen below. The total arm from the inputs is 392.9 inches for the Mooney M20J. Now to get the total moment, you add up all your moments, as seen below. The total moment for the inputs now is 138,531 inch-pound for the Mooney M20J. Now to calculate the new center of gravity with the inputs of weight we added, we take the total moment and divide by the total weight. CG equals total moment divided by total weight. So we take our calculations, 138,531 divided by 2,853, and we get 48.56 rounded. The new CG with the added weight is 48.56 inches behind the datum line for our Mooney M20J. Now, we're going to look at the center of gravity envelope for our Mooney M20J by using our graph like Miss Cindy Holman did during her video. Our total weight is 2,853, and the total moment we divide by 1,000, or 138,531 divided by 1,000 equals 138.5. Here's our weight limits again from our pilot operating handbook. And now to the center of gravity moment envelope graph. As we see, we plug in our weight at 2,853 on the graph. We plug in our total moment of 138.5. Now we connect the lines to see where it is. We notice the safe and suitable for aircraft envelope is shaded in the dark gray. And if you notice, we are out of the safe envelope. We are not suitable to fly for the Mooney M20J weight and balance standards. As you see using the graph provided from the left, we are way out of our center of gravity envelope for the Mooney M20J. Now let's see if we're within our center of gravity limits for our aft limit and forward limit by using the graph below from the Mooney M20J Pilot's Operating Handbook. we know the following. Total loaded aircraft weight is 2,853 pounds. The aircraft CG location is 48.56 inches positive behind the datum line. Note, see slide 13 for calculations. Here's our center of gravity limits graph from our pilot operating handbook. We plug in our weight of 2,853. Now we put in our 48.56 inches CG location. We connect the two lines to see if we're within the center of gravity limits. The shaded area in green is a safe and suitable for aircraft center of gravity limits. And as you can see, we are out of the safe center of gravity limits, and we're not suitable to fly for the Mooney M20J weight and balance standards within the pilot operating handbook. As you see, using the graph provided from the left, we are way out of our center of gravity limits for both the aft limits and the forward limits for the Mooney M20J aircraft. Now, to how has the passengers' fuel and baggage compartment weights affected the center of gravity for the Mooney M20J? As seen from the calculations and by using graphs from the pilot's operating handbook for the center of gravity envelope and the center of gravity limits, both aft limits and forward limits, the Mooney M20J aircraft is not suitable for safe weight and balance flight conditions. The pilot will have to either leave passengers behind or reconfigure the aircraft to make the Mooney M20J safe for weight and balance flight conditions. Professor Powers and Embry-Riddle Aeronautical fellow Eagles, this is my final presentation on the M20J Mooney aircraft. I hope you enjoyed my presentation. I'm looking forward to reviewing yours. And the final two slides are my reference slides for this presentation.